Hi everyone, and welcome to this quick Godot C# tutorial where we're going to talk about unit instantiation and random numbers. And before we jump into the tutorial, I want to give a big shout out to LuckyNot, who actually suggested this topic. So if you have some neat Godot concepts that you'd like me to do a tutorial on, you can suggest one too by dropping a comment down below. Okay, now by the end of this video, you'll know how to instantiate some pre-made scenes using C# code, and also how to use Godot's built-in random utilities to place or move units in a basic 3D scene. We won't talk about collisions or navigation, we'll just be doing transform-based translations, but we'll also discuss some quick tricks for getting better randomness in a video game. Of course, don't forget that if you want to get the files of this tutorial directly, you can have a look at the GitHub repo with all my Godot tutorials over here. And as usual, since we'll be coding our logic in C#, make sure that you have a version of Godot with .NET enabled. But now, with all that said, let's dive in and discover how to make and move units randomly in Godot and C#. Okay, now to start off, let's have a quick look at the scene and the assets that I prepared for this tutorial. Like in previous tutorials from this series, I'm going to use some assets by Kenny for this demo, and more precisely, I'm going to use his Space Kit. This pack contains a good amount of low-poly, cartoony, 3D sci-fi models, with both environment props and little spaceships, so those will be really neat for doing our little units. After I imported the GLB spaceship models from Kenny's pack, I used Godot's advanced import editor to replace one of the materials, which was a light yellow with a more vibrant and visible red. Then in the 3D scene itself, I pre-placed a few rocks and craters, and I added a basic ground plane with a simple orange material to get my background. I also added an Omnilight 3D node with fairly high range and energy values to get this point light in the middle and illuminate the entire scene. And last but not least, I added a camera 3D to actually render this whole scene. Because I wanted to keep a low-fi aesthetic and I wanted the scene to be clear and readable, I decided to go for an orthographic aerial view. So I switched my camera to an orthogonal projection, and then I simply increased its size to encompass the entire scene. I also made sure to create an environment resource in my camera node so that I could see my final render result inside the editor rather than having the default debug environment, and also to be able to change the color profile to ACS and get more interesting colors in the final visuals. Now you'll notice that in this scene I've left the middle zone empty, because that's where I want to create and move my units. And since we won't be talking about collisions or navigation, we need to have some sort of safe area so that it's not too ridiculous visually. And here, the central zone goes from roughly -6 to +6 on both the X and Z axis. Finally, one last important note is that in my hierarchy, all the environment stuff is put under a scene node, and then I have another basic node underneath called units, all in caps, which will be the parent node for all the unit instances when we create them via our script. So it's important that we know how this node is called, because we need to actually get it via a path in the C# logic. Of course, don't forget that all of this is available on my GitHub, so if you want to get this demo scene to start off the tutorial and work along with me, just look for the one marked as template in the folder. And now, with this in mind, time to prepare our unit prefab. So, as we said before, we're going to use Kenny's spaceship models for units. The goal will be to make a list with all of those models, and then pick one at random every time we spawn a new unit. But even if the model will change, it will still be nicer to have some shared structure between all of our units, typically if we want to give them some logic to move later on. So let's actually start by creating a new scene in our project with a 3D root node called unit, and save it as a new unit.tscn resource. And just to try it out and see how it looks, let's drag one of the GLB models from Kenny's pack in this new hierarchy. Okay, so the spaceship is really cool, but you see that it's not properly centered on the horizontal plane. So there's actually an offset between the origin of our unit scene and the position of our model. This is something really important to remember whenever you export 3D models to use them in a game engine. A format like GLTF or GLB or FBX remembers the offset your model had relative to the origin of the scene in the 3D software. But now, what if you have some pre-made asset that you don't want to re-edit yourself and that still has some unexpected offset, like we have here? Well, a basic solution is to use an intermediate node 3D to kind of counteract the offset. So let's call it mesh and put our GLB model instance inside as a child. Now the question is, of course, what exactly is this offset that we want to counteract? Although we could try and eyeball it by looking at the grid in the 3D viewport, a more robust method is to take a look inside the GLB asset itself. So let's click on the Direct Scene Open button, and you see that Godot tells us that any changes we make won't be saved directly on the asset. That's because the 3D models that we import are read-only. So basically, if we open them and change something inside, the actual model that we imported won't be changed. Here we won't be modifying anything, we'll just be taking a look, so it doesn't matter and we can simply click on Open anyway. So in this scene we get a nested hierarchy of a few nodes, with some extra node 3D node at the root that Godot auto-injected during import. To get the offset, we just need to select the mesh instance with the actual 3D shape, check out its transform position, and then take the opposite of this vector for a new mesh node position. So it will be -2 on the x-axis and -1.5 on the z-axis. And here we go! The spaceship is now properly centered at the origin. And the good news is that all the GLB spaceship models in Kenny's pack have the same offset. So now, whichever ref we instantiate under our mesh node, it will be properly recorrected to be at the origin of our unit scene. Alright, now with this little scene ready, let's see how to actually use some C# code to instantiate it at runtime and spawn units randomly in our scene. Because the core of this demo is the random unit generation, let's just add our logic in a C# script on the root node of the demo scene. Of course, in a real game, you'd probably have some subnodes to organize and separate your logic better. But here, it's okay, cause there isn't really any other logic anyways. So anyway, I'll rename the script to unitspawner.cs and then open it in my IDE. The very first step here is to add some variables for the unit generation. More precisely, we want to tell the script what the template unit scene is, what GLB models it can use to fill in this template with specific visuals, and how many units we want to spawn. In Godot, whenever you want to reference a TSCN file or a 3D model resource in a project, you need to use the packed scene variable type. And of course, to be able to assign it in the inspector, you need to expose it using the export attribute. Also, note that for the reference GLB models, we're actually using an array of packed scenes, because we want to give a list of possibilities to pick from. For the number of units to spawn, we can just use a regular integer with a default of 3 or 4, for example. And while we're at it, let's also set up some private constant integer values for the minimum and maximum coordinates on the x and z axis that match our central empty area, so the -6 to +6 units. Alright, now let's come back to the Godot editor and rebuild our project in the MS build tab so that the engine knows about our new exposed variables. As a reminder, that's because we're using C# and not JavaScript, so we need to actually compile the project for changes to be taken into account. With our new slots available in the inspector, we simply have to drag the unit.tscn scene to the unit prefab scene, and our GLB models to the units array. And then back in our script, it's time to use all of this to really create units. Okay, so since we're going to generate units when the game starts, but we might also want to regenerate them later on, let's extract our generation logic to a generate units function, and call it from the ready hook of the script. In this generate units function, we're going to do a for loop based on a number of units, and in each iteration, spawn a new unit in the scene. So first, we'll take our reference unit scene and call the Instantiate method on it. We can even use the C# generic type syntax to specify that we want to get it as a Node3D object. So this Instantiate method is basically a way to turn a packed-in variable reference into an actual node instance. And by specifying the type here, or by doing a cast, you can then get a specific component on your new instance. And now you can even set the name of this new node to a custom value, for example. However, for now, this node isn't actually added to the scene, meaning that we sort of have a new node floating about in the air outside of the scene tree. To truly add it and show it in the scene, we need to call addChild on our units subnode. This will put our new instance as a child of the units node. So this addChild function is what actually integrates the new instance in the hierarchy. The next step is where we're going to apply some randomness. But because we're on a computer, it's not actually going to be true randomness. Indeed, something important to remember is that computers don't really do complete randomness. Instead, they do what we call pseudo-random number generation, where you start from some specific value and then you just do some crazy calculations to produce new numbers that aren't too similar to the previous ones. The trick is that, as you can see, all those numbers taken as a whole do look pretty random. We can't see any logic that ties one to the other. But behind the scenes, this is all just a very strange mathematical progression that starts from one arbitrary point, which means that if you restart from the same point, you'll actually get the exact same weird series of numbers every time, which kind of defeats the purpose of randomness, right? So that's why it's called pseudo-randomness. Although they appear random, the random numbers generated by a computer actually depend on the origin point, which we call the seed, and the underlying algorithm that computes the next numbers. And since most of the time you can't really change this algorithm, the only solution to really get different results each time is to use a different seed. This is what Godot's gd.randomize function does. The idea is to call it just once at the beginning of our game, so typically here in our unit spawner's ready function, to set a new starting point for pseudo-random number generator, a new seed. By the way, note that if you're testing your game and you want to get fully deterministic runs instead of random ones, meaning that you want your pseudo-random numbers to actually be the same each time, you should rather use the seed function and pass it some arbitrary constant value. Okay, now that our pseudo-random number generator is initialized, we can use it in the generate units function. For example, for the position, we can create a new vector 3 and in the x and z coordinates, use gd.rangeRange to generate an integer position in our central zone. Note that this function will return a random integer if you give it two integer range values, and a double value if you give it two double range values. Then we can of course do something similar to rotate our instances randomly around the vertical axis, but we just need to be careful to actually convert the random values in degrees to radians. And finally, we can use another Godot random built-in called gd.randi for random integer and use a modulo with our total number of ref models. So this line gives us a random integer between 0 and this value. So it basically gives us a random index of the model to load. So all that's left to do now is instantiate this packed scene by picking it from our array of references and add it as a subchild nested in our new instance of the unit scene, inside the mesh node that we prepared earlier. And so that's basically it. If we run our game from the demo scene, you see that when it starts, we now have a few spaceships that have spawned in the middle of the map. Though, to make it easier to test our logic and see the positions indeed change every time, we should prepare a basic debug system with a button that triggers a respawn of our units. So to set up this debug, let's go ahead and add a reGenerateUnits function in our script that simply empties all the previous children in the units node and calls the generateUnits function again. Then we'll rebuild our project and create a very basic UI with a simple button inside. Note that if you're curious about how to do this exactly, I've actually discussed the fundamentals of making UIs in Godot in this previous episode of the series, so be sure to check it out. Here we'll leave the default button options and just change its label to generate. And then finally we'll link its press signal to our new reGenerateUnits function. And here we are. If we restart our game, we now get some initial random units, and then we can click on our debug button to recreate new ones and check that the positions and rotations are indeed different each time. However, you also see that quite often our spaceships actually spawn on top of each other. And that's because, for now, our random positioning logic is a bit too basic. Okay, so at the moment we've set up a very basic random positioning. We're simply computing a random x coordinate and a random z coordinate for each unit. The problem with this technique is that you don't really check if there was another unit in this spot already. And here, given how little space we have, the chances of this happening are actually pretty high. To solve this issue, there are two possible techniques. One, we could store the already used positions as we compute them, and then use a do-while loop to ensure that we don't reuse them for the next units. Or two, we could use a list of random unique positions and pick from this for each unit. I'm personally a fan of the second technique, because I'm always a bit afraid with while loops and I always fear they're gonna run for too long or even crash my program. So here I'm gonna go for the list of random unique positions solution. Okay, now in our case, applying this technique means pre-computing all the 169 possible positions, because we have 13 possible values on the x and z axis, and then shuffling them in random order. Then we'll just need to pick the n first ones, where n is the number of units to place, and we're absolutely sure that all of those n units will have their own spot. Now, in truth here, I'm not even going to compute 169 positions, because to be sure that there's enough space between the units, I'm going to skip some of those points, and instead just take 1 out of 4 in each direction. So actually, I'll have just 16 positions in total to shuffle and assign. Computing these positions is really pretty straightforward. We just need to prepare a Godot array of integer vector 3. Those are just like basic vector 3, except that they don't contain a float value with decimals but integer values. And then, in the ready function, I'll go through the central area with steps of 4 along the x and z direction. So this way, I'll go through all the possible positions and I can just add them to my list. So at the end of this double loop, I have my 16 positions in order from the -6 point to the +6 point. Now, in our generateUnits function, we can simply use the super cool shuffle method that's available on any Godot array to make sure that our positions are re-randomized every time we run our function. And then, in our loop, instead of making up a new vector 3 on the fly, we'll take the position inside our array at the current index. And that's it, problem solved. You see that now, no matter how many times we regenerate our units, they're never in the same spot. Alright, so our unit spawn logic is now ready. To wrap up this tutorial, let's see how to add a bit more of C# to also have our units move to some other random spots on the grid. In this last section, we're going to see how to give random target points to a unit and have them navigate to them with a simple translation-based scheme. Again, we won't be talking about physics-based movement, like we did in those previous tutorials of the series, for example, or about navigation. But as usual, if you want to learn more about these topics, typically about unit navigation in Godot 4 and C#, feel free to drop a comment down below. Okay, now the idea will be pretty simple. Instead of just assigning a random position from a list to our units, we'll give them a random target position from the list. And then we'll have a script on those units that has them move if they're not currently at their target position. So let's start with this unit script. So we'll just create a new script on the root node called unit.cs and open it in the code editor. Okay, so first, let's declare a constant float value for the speed, because for now we'll just assume that all the ships go at the same speed. And then we'll also prepare a vector3 variable to store the target position. Now, to be able to set this target position from our main unit spawner class, let's create a public function called setTargetPosition that receives a vector3 value and assigns it as the new target position for our unit. Plus, it will also allow us to automatically have the ship face the target position by using the lookAt method. This function allows us to rotate our object instantly so that it looks at a given vector3 position with a given up vector. Here we can use the global up vector. Now that we have this function, we can go back to our main class and do two things. First, in the generateUnits method, we need to assign the target position of our units to their current position. Otherwise, when we start the game, they'll basically move towards the default vector value, which is the origin point. Then we can create a new function, for example, moveUnits, that gives our units new random target positions. It's very similar to the rest of our logic, so first we'll reshuffle our list of positions, and then we'll iterate through our current list of units, and for each, assign the new target position. Of course, if we rebuild our project, we can then also expand our debug tools by adding a second button to the UI and connecting its pressed signal to our new moveUnits function. However, for now, our units won't actually move anywhere, because they're not doing anything with their target position. So let's go back to our unit script and handle the movement routine. To do this, we can use the process function, which runs every frame. We just need to compute the difference between our target position and our current position. And then, if this vector difference has a length above a given arbitrary threshold, we'll translate our unit in the global space along this direction, meaning our difference normalized, at the speed value and re-multiply by the time delta. So the important thing here is that we can just check if our current and target positions are exactly the same, because with floats, there's always a little bit of variations, because basically you can have some micro decimal that is a tiny bit different, and thus a simple equal check will usually fail. So if we were to use a not equal condition, we'd have some infinite little oscillations around the target point, with the units vibrating a little and computing ever smaller displacements but never really stopping. So by using this threshold, we're saying that if it's close enough, meaning it's not visible by the human eye, then we just say we reached the target point and we stop computing new displacements. Okay, now there's just one thing left to do, and that's in the setTargetPosition, before doing the lookAt, check whether we're actually supposed to move away from our current position. Cause with our system, you'll notice that nothing prevents us from reassigning a unit a target position that is its current position. And in that case, obviously, looking at your own position doesn't really make any sense, and Godot won't like it too much. So let's just copy our checks from the process function so that we only do this bit of logic if the unit is supposed to move. And there we go. If we run our game again, you see that we now have our random units that stay still at first, because they are targeting their current positions. But then, as soon as we click on the Move button in our debug UI, they start to move on our grid. And the nice thing is that, thanks to our improved randomness, we're absolutely sure that no two units will ever aim for the exact same spot. But anyway, here you are. You now know the basics of spawning and moving 3D scene instances with some randomness in Godot and C#. I hope you liked this tutorial and that it helped you understand the basics of spawning via code and improving on naive random. If you enjoyed this video, feel free to like it, and subscribe to the channel to not miss the next ones. And of course, don't hesitate to leave a comment with ideas of Godot tricks that you'd like to learn. As always, thanks a lot for watching, and take care.